Okay, welcome back, everybody. Moving on to chapter 2 on the book. I'm calling it the discrete calculus. In a lot of ways, this is the first chapter that's going to differ from maybe a regular second semester calculus course. I mean, all the topics technically are the same, but really our perspective on these topics is going to be considerably different. And so here you can already see within the first section, sequences and indexing. There's always going to be a section like this in kind of a regular Calculus 2 class. But I'm associating sequences and indexing to something called a discrete calculus. And so really we're going to try to do calculus. And by calculus, I mean derivatives and integrals. With this new object called sequences. And maybe you've seen sequences before and maybe not, but it's an object very similar to a function, or maybe the continuous functions and differentiable functions we've seen in regular calculus. But sequences, they don't move continuously from one part to another the way that we expect regular functions to behave. So we're going to start with the definition of a sequence, which I've got here. And I do say that a sequence is a function because if we jump back all the way to the kind of the preliminaries chapter of the book, we defined functions as maps which have a domain, a codomain, and a rule which assigns an element of the domain to an element of the codomain. And sequences are satisfy that criteria. It's just that in traditional calculus, maybe our functions look like f of x is x squared minus 2x plus 2. And this function's got a domain and codomain, which are the real numbers. Sequences, the domain is going to be some subset of the integers, okay? So rather than working with, the real number line, maybe I start here at 0 and I end at pi as a domain of my function. Now my domain is some subset of the integers. And if we don't remember this notation, here I've got n min and n max. The notation with the double square bracket, this is just going to refer to intervals of integers rather than intervals of real numbers. And so if n min, let's say for example, n min were -2 and n max were 3, then kind of this double bracket -2 comma 3 idea is really just going to be a set of points, -2, -1, 0, 1, 2, 3, or thought about like the real number line. The set of points is just 1, 2, 3, 4, 5, 6 points, interpreted as -2, -1, 0, 1, 2, 3. There's no continuum, right? I can't draw a line between those points. They're discrete, and that's where this word discrete calculus comes from. And so a sequence is a function whose domain happens to be kind of the set of integers, and the codomain can really be whatever we want still. It's just a sequence is special in the fact that what it's taking inside of it are subsets of integers. And so they're going to look the same just as regular functions. They have their domain and codomain as well as their rule, which assigns an element of the codomain to the input n. Kind of the more important thing that we want to think about sequences, and this is what mathematicians really attribute to sequences, is that they're ordered, right? In some sense, I could write down a collection of objects, 1, -3, and 4. So there's three numbers in, at least interpreted as sets, which I know we haven't really studied much, but at least interpreted as sets, it's perfectly valid to exchange the ordering. Exchanging order is valid for sets. But that's not what we're working with today. So maybe eventually if you take some future math classes, you would encounter sets a little bit more often. Exchanging order is perfectly valid for sets. It turns out it's not valid for sequences. So, these are not going to be equal to each other. We somehow assert that there's an ordering here. We could call this F1, F2, and F3 because there are 3 elements in the set. We could say F1 equals 1, F2 equals -1, and F3 equals 4. So that, the fact that we've given this collection of 3 numbers kind of a function which maps to them from the numbers 1, 2, and 3, we can kind of attribute the ordering of 1, 2, and 3 to the numbers 1, -3, and 4. I've already kind of covered this, but sequences are also discrete. And by discrete, really, even the English meaning of discrete is that the distance between 2 consecutive terms is a whole number. We're not continuum. You can draw the entire graph without picking up your pencil, and you just can't do that if you're trying to draw sequences. So that's what it means to be discrete instead. Now, as with every section of the book, I like to reinforce that even though these are mathematical concepts, we don't necessarily have to attribute numbers to the mathematical concept. So here I'm calling it a non-numerical sequence. I mean, by definition, the input to a sequence, right, or at least the definition we're working with in this class, the input to a sequence does always have to be numbers. They do always have to be a subset of the integers. But the output of the sequence, right, the output of the sequence could be non-numerical. So in this case, great example, of a sequence, I could define my sequence, which really is the rule of the function. So I define f of n, well, it's equal to m when n is equal to 1, it's equal to a, when n is equal to 2, it's equal to t, when n is equal to 3, it's equal to h, when n is equal to 4. So we just think about this as some map from the number 1 to m, from the number 2 to a, from the number 3 to t, and from the number 4 to h. And then because we've given it an ordering, really the sequence is, interchangeable with the English word math. So very nice little example, because we couldn't have something like Amhut is going to be, an anagram of the word math. This is, we think about this in English, they're not the same thing, right? These should not be the same thing, and sequences are what allow us to do that. They allow us to give some ordering to elements. So we can also generalize this to really say that any work of English literature is a sequence. So I've just grabbed Romeo and Juliet here, for example, which begins two households both alike in dignity. And of course it continues from there. And we could arguably define a function. I actually counted how many characters, including spaces, are in the entire play of Romeo and Juliet. Turns out there's 135,352 characters there. Not people characters, but like English letters and spaces and commas, etc. So those characters, and you could assign a sequence G, which maps from this subset. This is still a subset of Z, and recall that Z is the same thing as the integers. So it's a subset of the integers, and we could just make the output the alphabet as well as some other grammatical characters. And how does G get defined? Well, here it is. G of n is T W O space H O U S E H O L D S comma and so on. And in fact, this sequence notation, sequences, or really sequencing, is exactly how, if you've never taken a computer science class, this is exactly how computers store works of literature, and of course so many other things than that. I mean, your entire computer, your entire phone is really running on sequences right now. So it basically stores everything, but including stores works of literature. So inside of the memory of really probably some cloud device, if that's where you're going to extract the works of Shakespeare from. But inside that memory, there is like truly a mathematical sequence sitting behind everything, such that if you decided you wanted to read it, it's going to basically grab the sequence and show you kind of a subset of the output of the sequence. That's what it's going to display on the phone. But there's some other code to make it, of course, show up a little prettier than what I've drawn here. And then I've got another example here, other ordered lists. Think of any sort of ordered list that you have in your life, so schedules, calendars, batting orders, etc. They all satisfy definition of sequences. So as long as something's got like a prescribed order to it, and you're going to interpret it as an ordered list, that's what a sequence is. Now, we will be working with numerical sequences. I mean, especially if we're going to try to do calculus with any of this, it would help if the outputs of our sequences are numbers. So we will work with numerical sequences. A lot of numerical sequences have this thing called a recursive definition. It's just a very effective way of us to actually construct numerical sequences. It's a useful tool we have to construct them, as opposed to with continuous functions. We often rely on polynomials, exponential functions, logarithms, trigonometric functions, etc. With sequences, we do rely on those quite often, but we also rely on these things called recursive definitions. And so what is a recursive definition? Well, it allows a sequence's nth term. Okay, so this is, if I'm defining f of n, so that nth term, it can be defined, with respect to the prior terms. So, what does it mean to be prior? What comes before the number n, for example? Well, the number n minus 1 comes before it, the number n minus 2 comes before it, the number n minus 3 comes before it. And so it turns out to be useful to refer to kind of previous terms of the sequence. There's always an interpretation. Like, you can start the sequence somewhere, and if you start it somewhere, you know where it starts, then you just have these definitions based on previous terms, so you can kind of compute each next step in the sequence recursively. This is the word we use. And so, you require that at least some of the first values are themselves defined independent of recursion, but after that, everything else you can kind of, we use the word iterate, so you can kind of iterate future terms from the first couple. So I've got some examples of numerical sequences here, in fact, recursively defined numerical sequences. I think most mathematicians' favorite sequence, or at least one of the ones they would love to introduce at the beginning of the sequence section, is the one I've introduced first here. This is called the Fibonacci sequence. And you'll notice I really am relying on function notation here still, at least for a short term. We'll see that there's a different notation we can use in a bit. But for now, I will rely on function notation. So I still have, my function f, which has a domain, which happens to be the natural numbers, and a codomain, which also happens to be the natural numbers. And we're going to define it recursively. How are we going to do this? Well, here's my function. There's my defined equal sign. What am I going to do when I read these off? This is really, phrased as a piecewise function would be when you've encountered those in the past. Let's read the bottom first. It says 1. So my function is defined to be equal to 1 when n is the number 1 or 2. So that means, right, n being the input. So if the input to the function is 1 or 2, we're just going to let my function be 1. And then if the input to my function is anything bigger than or equal to 3, so some future inputs, this is where recursive definition comes into play. I'm going to take fn minus 1, and let's think about what that means. This is the previous term, because n minus 1 is 1 smaller than n, and then n minus 2 happens to be 2 terms ago. So previous term, 2 terms back. And what else do we do? Well, we've got the plus here, so I'm just going to add the previous term to the term 2 terms back, and that's what gives me the next term in the sequence. So in some sense, this is like, jumping back even to the very first day, we talked about things, translating math to English. This mathematics, it looks kind of ugly, but it's a dense and useful notation to say that we're going to define a sequence of numbers whose first 2 terms are 1, and for all future terms, we're just going to add the previous 2. So that's really what this is saying if we want to interpret this as mathematics translated into English. And so thinking about it that way, we go ahead and calculate the first terms, quite a few of these terms. And we know that the first 2 terms are both 1, so we're not too worried about those. But what comes after that, if I've got 1, comma, 1, comma, I'm going to add those 2 terms together to find f of 3. So there's 1 plus 1, they add to give me 2. I'm going to then add the next previous 2 terms, which in this case is 1 and 2. There's my 1 and 2, that's going to give me 3. As my 4th term. I'm then going to add the previous 2 terms, which happen to be 2 and 3 in this case. There they are. Gives me 5 as the next term. I'm then going to add the previous 2, which happen to be 3 and 5. Here's 3 and 5, gives me 8 as the next term, and so on. And this is what we call the Fibonacci sequence. If I can remember how to spell his Italian name. Fibonacci sequence. There you go. Very cool sequence. We'll see in some exercises that it has some useful properties. People like to find it in nature a lot. It turns out, especially if you compute it out to very large terms, there are some elements of nature which mimic those numbers, especially kind of in the way that plants decide to distribute their petals around the center, or pine cones distributing their scales. I believe that's the word for it. Scales around the center as well. So in nature, the Fibonacci sequence can be common. It's somewhat overblown how common it is, but there are definitely cases where it will show up in nature. And I've also got this nice little flow chart to kind of show how we're recursively defining things. So if you recall, we started with the 2 terms 1, and then these 2 terms add together to give me 2, and then the previous 2 terms add together to give me 3, and the previous 2 terms add together to give me 5. Then we would end up with 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, and so on. So I kind of like the flow chart there. Our next recursively defined sequence can be the factorials, which we've actually seen before, right? That's, this number that we've defined, n factorial with the exclamation point, and it was originally defined by, n times n minus 1 times n minus 2 times ... times 2 times 1, right? That's how we define the factorials in the past. I'm claiming you can define them as a sequence recursively using the following recursive definition. So what does this say? It says if I start at 0, then the 0 factorial should be 1. And I realize I've written it as g of n. I'm trying to reinforce that it is a function from the natural numbers to the natural numbers. But recall that 0 factorial was equal to 1. And then how do we find the next factorial for every n greater than or equal to 1? Well, we take the previous factorial. This is saying previous factorial, and we go ahead and multiply it by our new number. If we're trying to find the 5th factorial, we're going to take the number 5, multiply it by 4 factorial, and so on. So I'm claiming that we can do it this way. Let's just verify that really quick. Well, we know that 0 factorial is equal to 1, and we know that 1 factorial is equal to 1 times 0 factorial. Just think, every time you see this g, replace it with the factorial symbol, the exclamation point. Like I said, I'm only including it as g to really reinforce that this is a function. But we're going to take 1 times 0 factorial, which is 1 times 1, and we all know that 1 times 1 equals 1. And so, 1 factorial is equal to 1. For 2 factorial, we can go ahead and take 2, and we're going to multiply it by 1 factorial. Well, 2 times 1 factorial is 2 times 1, which happens to be 2. For 3 factorial, we're going to take 3 times 2 factorial. And we just found 2 factorial was 2, so we're going to take 3 times 2, we're going to get 6. Well, for 4, we'll take 4 times 3 factorial. We just found out that 3 factorial was 6, so 4 times 6, we get 24. 5 is going to be 5 times 4 factorial. We just found out 4 factorial is 24, so 5 times 24 is 120. And so, yeah, the factorials can be defined recursively as well. And I've got the nice little flowchart here that's saying at each step along the way, we're not combining 2 terms, we're only looking at the previous terms. There's only the 1 arrow here. But the arrow is saying multiply by 1, multiply by 2, multiply by 3, by 4, by 5, by 6, by 7. And we end up with all the factorials. We also have the triangle numbers here, which I also do define in one of your exercises, maybe a little bit more explicitly, so look forward to that. Triangle numbers happen to be a sequence whose first term is defined by 1, so the n equals 0 case is defined by 1, and then each previous term, or each future term, is equal to the previous term. and then I'm just going to go ahead and add the current number that I'm sitting at. So I look at the previous term and I add the number that I'm sitting at. So we start at 1, easy enough, and then to get to the next term, well, to find term 2, I'm going to take the previous term, which happened to be 1, and I'm going to add 2 to it. So 2 plus 1 happens to be 3. To find the third triangle number, I'm going to take the previous term, which happened to be 3, and I'm going to add 3 to it. So I have 3 plus 3 gives me 6. To find the next term, which happens to be the fourth term here, I'm going to take, n equals 4. I'm going to add the previous term, which happened to be 6. 4 plus 6 happens to be 10. To find the fifth entry, I take the current term I'm looking for, the fifth, plus the previous term, which was 10, and I'm going to get 15. And so this is very similar, actually, to the factorials, even in the flowchart, because I just take the previous term and I do something to it. It's just that in the triangle numbers, well, back to the factorials, I was multiplying by that specific term number. In the triangle numbers, I'm actually adding the specific term number. So, plus 2, plus 3, plus 4, plus 5, and so on. You could jump back. We could have defined this as 0 right away, and then a plus 1 if we wanted to. Then it looks more like plus 1, plus 2, plus 3, plus 4, plus 5, and so on. So there's some good examples of kind of recursive definitions of sequences. Not that those are the only ones you'll see, and we will encounter some kind of basic definitions of sequences, which are equivalent to the definitions of functions, like n squared plus 2n plus 2 is a great example. But recursive definitions can kind of give us a broader collection of definitions if we want. So we're going to switch over. I've been using this h of n, or up here g of n, or up here even f of n, to really reinforce that these are functions from a subset of the integers into some codomain. In fact, most of the time when we encounter sequences, it's not notated in that way. It's notated in a way called indexing. And so that's why the title of this section was Sequences and Indexing. I wanted to cover sequences, what they are, but there's a very specific notation we often use, and that notation is called indexing. And if we think about what this word means, index, an index is really like a specific number which references something else, right? You go to the library, or at least in the past before we had internet catalogs for libraries, and we would go to the card catalog in the library, and then the card catalog would give us a specific index on truly an index card. That's why they're called index cards. Now you know. So that's what index cards were, and it would index the collection of books in the library. So that's where this word indexing kind of relates back to, but it's a different notation on sequences. So here at the very bottom, let's just jump to the bottom where I'm looking here. This f here, which is my function, which happens to also be my sequence. What have I done to it to index it? I have put the sequence, and this is really the sequence rule, right? So it's just the rule of the sequence inside curly brackets. And I've also assigned variables and bounds to the right hand side, right? So on this right hand side, I've got some variables. Well, my variable here was n, and some bounds, and min, which came directly from the domain of the function, and max, which also came from the domain of the function. So in some sense, this indexing incorporates the rule, and the domain of my function all as one kind of larger piece. We pay the price of curly brackets, but we've got this subscripting and superscripting going on inside of the indexing. But there's also something else that's showing up. If I look to the left-hand side here, on the left-hand side here, I've taken, rather than writing f of n, like an input to a function, I've actually taken a new letter. In this case, I'm using a, and a tends to be quite common for sequences. So I'm using a new letter, a in this case, to represent the sequence. And rather than placing n, my variable, inside of a function, I place it in a subscript. And the way we interpret this is really that, like, a, in some sense, is a collection of numbers, because, you write constants, arbitrary constants as the letter a often enough. It's like a collection of numbers which, as n changes, that specific number changes as well. That's kind of the way you interpret a sub n, which is the way I would say it out loud, is a sub n, sub meaning subscript. So a sub n meaning a subscript n, meaning a sequence, but the sequence just gets defined by, an actual function, and we have our lovely function notation which defines it. But that's not really what we end up seeing out in the wild. What we see out in the wild is something along the lines of this, where we say, oh, a sub n, indexed by n equals 0 out to n equals infinity, is defined by 2 to the n. Not really a surprise that you just define it by some notation. And then we can interpret kind of this curly bracket notation here by, well, what's going on here? The 1 is 2 with a 0, the 2 is 2 to the power 1, the 4 is 2 to the power 2, the 8 is 2 to the power 3, and so on. We would just take all of the powers, powers coming specifically from, well, we're starting at 0 and we're ending at infinity, so we're just going to plug each of those values into our definition 2 to the n and kind of extract this sequence on the right hand side. And of course, if you ever want to kind of call out specific values, you can. You don't always have to write the entire sequence out the same way I could just write, f of 8 equals 24 in some random setting. You don't have to always write out the entire sequence. You can also just specify a specific subscript and say, by the way, a sub 4 happens to be 16, or a sub 3 happens to be 8. Where does the 16 correspond to? Well, it's the 0, 1, 2, 3. It's the 4, right? The 4 subscript there. It's the fourth entry in that sequence, even though we start at 0, so you interpret 4 correctly. We've also got something like the odd number sequence if we want. I'm just providing ample examples here to make sure that we know we can define a broad array of these sequences. So, b sub n we can define as 2n plus 1. And if we go ahead and plug in 0 to 2n plus 1, that's 2 times 0 plus 1, which happens to be 1. If we plug 1 in, 2 times 1 plus 1 happens to be 3. If we plug 2 in, 2 times 2 plus 1 happens to be 5. If we plug 3 in, 2 times 3 plus 1 happens to be 7. And so that's how we would just construct the sequence 2n plus 1 and going from 0 to infinity. Similarly, we can call the next sequence, which I'm in this case calling c sub n, the alternating sign sequence. Why is it an alternating sign? Well, it's been defined as -1 to the nth power. What happens when I take, by the way, my domain being 0 to infinity, -1 to the 0 power? Well, that's 1. -1 to the first power is -1. -1 squared happens to be 2 copies of -1, also known as 1. -1 cubed is 3 copies, also known as -1. And so it's called alternating sign because, the true sign of plus, minus, and so on just keeps alternating as the sequence moves forward. I call that the alternating sign sequence. My next remark is just to say that we do often drop the brackets and index set on sequences. So if I jump to the top here, where I've got a sub n going from 0 to infinity, and then I write this all out, rather than defining the entire sequence as the entire sequence of 2 to the n, I can get away with just saying, oh, by the way, a sub n is defined by 2 to the n. This is kind of the equivalent to writing a function without its domain and codomain, right? We often just write this as a function, even though that's technically only the rule of the function. It needs to be paired with its domain and codomain. We'll just write like a sub n is n squared plus 1, and we should be clever enough to interpret that as a sequence, even though I haven't given it its special brackets. So that's just something I want to say, help out with context. Anyway, super short video, well, relative terms, short video. Next video, we're going to move on to actually doing some calculus with these objects, which is what's really exciting. I'll see you then. I hope you look forward to it. Bye.